Hey guys, welcome to DataTrek, your one-stop channel for all the data science and machine learning updates. In today's video, we will be looking at DeepSeek's R10 and R1 model. These models are making a lot of buzz and they are performance-wise on par with OpenAI's reasoning models, and as well as these models are trained on marginal of the cost of what OpenAI's or other companies' LLMs are trained on. So what were the technical innovation DeepSeek did that enabled them to make a reasoning model as good as the competitors, OpenAI's and other big providers, and as well as how they were able to just train these models, foundational models, in marginal of the price. We'll look into that as well. So with that, let's get started. DeepSeek is a Chinese artificial intelligence company and they have developed two notable models, DeepSeek R10 and DeepSeek R1. Both models are designed to enhance the reasoning capabilities, but they differ in their training methodologies and their performance characteristics. Both the models are built on DeepSeek V3 architecture. So R1 and R10 are built on DeepSeek V3 architecture. V3 was released in December 2024 and R1 models, the R10 and R1, were released in January 2025. Something interesting, let's look at the technical report of DeepSeek V3. DeepSeek V3 is a strong mixture of expert language model. So we'll look at that, what mixture of expert is, and it has 671 billion total parameters. Even OpenAI's models have these many parameters only, but the interesting thing is only 37 billion activated parameters per token. So per token, not all the parameters are getting activated because it's a mixture of expert model. We'll look into that, what that is, but the key thing to take away is not all the parameters gets activated per token. And they have used advanced techniques like multi-head latent attention. We'll look into that. We'll look at the DeepSeek MoE architecture as well. And another interesting thing to look at is they pre-trained DeepSeek V3, which is in the pre-training you do next word prediction on 14.8 trillion diverse and high quality tokens. It may be from different languages and so on. So it's a very diversely trained model. And followed after the pre-training, there is supervised fine-tuning and reinforcement learning. We'll look at all of that into details. And it's trained on H800 GPUs. It took 2.8 million H800 GPUs hours. So I was just doing some calculation that if it takes 2.8 million H800 hours, how many days it would have taken to train these models. So my calculation is something like this. If you take 5,000 such H800 GPUs and you train it for 24 days, 24 hours, it will come near to 2.88 million training hours. So if you are training for 24 days, 24 hours with 5000 H800 GPUs, you will be able to train it. So it will take 24 days given that you have 5000 H800 GPUs. And also let's look at why is the cost so low. The cost is low because out of that 2.8 million hours, 2.6 million hours goes in pre-training, which is the next word prediction. 119,000 hours goes in context extension. And 5,000 hours goes in post-training, which is supervised fine-tuning and reinforcement learning, and the price is $2 per GPU hour, so it comes out to be around 6 million. So only in $6 million they were able to train a reasoning model as good as OpenAI's own model in terms of reasoning capability, so which is pretty impressive, and that's why it's making a lot of buzz. And in the pre-training, what happens? It's a next word prediction on 14.8 trillion tokens. English, Chinese, math, programming, all these type of tokens were used for the pre-training. In context extension, you increase the context length so that from 32,000 to 128K, so that it is able to handle long sequences of text. Let's say you give it a long code and ask questions, it will be able to handle because there has happened a context extension which enables it to handle long input text. And then there is post-training where the alignment towards more human preferences happens. The model is first trained through supervised fine-tuning and then reinforcement learning. In supervised fine-tuning, the model is tuned to samples to improve reasoning. Like it's a question answering kind of data set, and maths, programming logic, non-reasoning questions like creative writing, question answering via expert models and human verifications is used to do the supervised fine-tuning. And in reinforcement learning, you enhance the reasoning and alignment with human preferences. There are ways to do reinforcement learning like PPO, group policy optimization. They use GRPO, which is an optimization or improvisation over PPO that was used by OpenAI. We'll look into all those things. So this is the DeepSeek V3 architecture. It uses mixture of expert, multi-latent attention, trained on huge diverse token, and as well as it takes about this much hours to train. and R1 and R1 zeros are trained on top of DeepSeek V3 architecture. Now let's talk about DeepSeek R1 0 and R1, the models which are trained on top of DeepSeek V3 architecture. R1 0 training approach, what happens is, in the post-training step, in the post-training we know that supervised fine-tuning and reinforcement learning happens, right? In R1 0 model, they didn't do any supervised fine-tuning, they directly did reinforcement learning. So the model was trained exclusively through large-scale reinforcement learning without any supervised fine-tuning. And the RL process relied on self-generated signals like self-consistency, mathematical correctness, or reliable rule-based verification. So basically, if given a question, whether it is able to think or not, like there are think tags in the answer or not, and final answer, is it very matching with the actual answer or not, like finally the math problem will have an answer, right? So are the two answers matching or not, and how it reads that answer, whether there were think tags or not. So in this kind of reliable rule-based verification, mathematical correctness, self-consistency, the model will get the rewards. And all these have to go through the chain of thoughts, that it should not directly emit an answer, it should have those chain of thoughts to finally come up to the answer. And if it is doing that, then it will get higher reward, and in this way it will the parameters will be moved towards the more better answers which are matching with the human preference. And that is what reinforcement learning is. This enabled the model to develop reasoning behaviors such as self-verification and reflection. The challenges are that because it didn't had that supervised fine-tuning, it faced issues like repetitive outputs, poor readability, and language mixing. And all of this happened because of the initial supervised training data. The initial question answering was missing. It just tried. The challenges occurred because the important step of supervised fine-tuning was missing, and they directly tried to optimize on reinforcement learning. They took the model after pre-training of next word prediction and tried to do the post-training based on just reinforcement learning. That's why the model emitted some repetitive outputs. While DeepSeek R1, to address the limitations of R1 0, it incorporated cold start phase, where in human annotated question answering dataset, the initial fine-tuning happened, which is supervised fine-tuning. Question answering, it is able to, given the question, it tries to learn what the answer should be, right? And we provide that answer in the target variable. So this combination of supervised fine-tuning and RL enhance both reasoning performance and output quality. So what happens once you do the question answering training or fine-tuning, which is the supervised fine-tuning, on top of it you do reinforcement learning to better enhance the reasoning performance. That is, if model is now able to answer the question, but is it more reasonable answer or not? Is it doing the chain of thoughts, mathematical correctness, self-consistency, are those things happening or not? That RL tries to further fine-tune the model towards human preferences, which is more reasonable way of solving a problem. And DeepSeek R1 achieved performance comparable to OpenAI's O1 model, which is the best reasoning model out there, and in tasks including mathematics, coding, and general reasoning. Now, next question: why DeepSeek performs so well while being cheaper to train? Because of multiple techniques they used. First is mixture of expert, then they used multi-head latent attention, they used advanced quantization techniques, they used multi-token prediction for enhanced performance, and they used reinforcement learning. So these are the 5 main techniques that led to very good performance at cheaper cost. So let's see the first one, which is mixture of experts. So in mixture of expert frameworks, what happens is there's a neural network architecture that dynamically activates only a subset of parameters for each input. So that's why we said, even though there are 671 billion parameters in the model, only 37 billion parameters are activated per token. So what happens is that depending on the input, only a subset of tokens get activated. The model is divided into several small expert models. For example, let's say there is a expert model for punctuation, verbs, conjunction, and numbers. Now whenever the user asks question, what is 1 plus 1, this is a mathematical question, and maybe the mathematical expert model will be able to answer it better. So it will be passed to the numbers expert model, and that model will get activated instead of all the models. So the model is divided into several small expert models. A separate network called the gating network, this is the gating network, which learns to select the most relevant expert for the user input. And since there is only few parameters getting activated, few models getting activated, few experts getting activated, there is a sparse activation. Instead of using all expert at once, the model activates only a few, in let's say 2 out of 16 experts for each forward pass. Hence it reduces the number of activated parameters per token, and training is cheaper because it is not training on all the parameters. Now only few parameters are adjusted, which are the activated ones. So there is a reduced computation per forward pass, because unlike traditional dense model that use all parameters for every input, mixture of expert only activates a fraction of them, and scalability without linearly increasing cost, right? Because MoE enables scaling of large parameter size model. A model can have hundreds of billions of parameters but still operate efficiently by only using a subset of model at any time. And it's an specialization of expert. Each expert specializes in different type of task or data distribution. This leads to better learning efficiency and higher model performance per parameter used. For example, in this case, the mathematical model is good with numbers, the other models are good with language, and so on. So each expert is good at its task, so there is higher model performance per parameter used, and definitely lower training cost, because since fewer parameters are used in training, the memory and computational requirements are significantly lower. This reduces the need for expensive GPUs and power consumption. So this is the overall DeepSeek architecture, where you can see that it uses multi-head latent attention. There are multiple experts, and there is a gating mechanism which activates only few experts, and so on. So next thing we will look at multi-head latent attention. The next big improvisation that DeepSeek did was multi-head latent attention. We know that transformer has multi-head attention, but multi-latent attention, what it does, it's an improvisation over multi-head attention, and it reduces the cost by moving attention calculations into a smaller latent space before projecting back to the full model dimension. So what happens in self-attention? Each token attends to the neighboring tokens, and finally the output attended vector of each token is produced, which is after weighing the weightages of nearby tokens. This is the entire process of self-attention and multi-head attention. But in case of multi-latent attention, we do all those calculations in smaller latent space, but finally we project back to the full dimension space. So final self-attended output vector will be of same dimension as in multi-head attention, but the calculation will happen in smaller latent space. This significantly lowers parameter count, betters the memory usage and computation, and makes it more scalable alternative to standard multi-head attention, especially in large transformer models. Before understanding the multi-latent attention in details, let's briefly touch upon self-attention. What is this self-attention in transformer which changed the entire trajectory of AI, which led to the birth of LLMs, chat GPTs, and so on? So what is attention mechanism? It means that the input will attend to the nearby tokens and then produce a attended output. The self-attention changed AI forever. Before self-attention, we used to have simple attention mechanism in models like RNN and LSTM. The problem was it was sequential nature, it was slow, the memory was shorter, and multi-word relation. It was able to handle the multi-word relation when the relationship was more in the neighboring words, but if there was some long-term dependency, it was not doing very well. So multi-word relation was limited. It was hard to scale because of sequential nature, and it was used in a smaller model, limited task, and so on. What transformer did was it brought the idea of self-attention, and it fully parallelized it. Basically in transformer you provide all the inputs at once and you have the position embedding. So because of this parallel nature, it fully parallelized the way in which we were providing the input. So self-attention was able to have long range understanding, it was able to capture global context, it was able to work with billions of parameters, and it led to the discovery of LLMs like GPT, BERT, DeepSeek, and so on. So now let's understand the difference between multi-head attention and multi-latent attention in more details. So first start with multi-head attention, which is the attention mechanism which was introduced in transformer. We have a sequence of length n, and each token, each word or word sometimes can be broken into further tokens. So each token will have a dimension of d. So let's call it d model. So we have n words, n tokens, and each has a dimension of d, which is d model. Now what we want to do is for each of these input tokens, we want to produce a self-attended output vector. Now how the self-attention works is to reach to that state where for each token we have a self-attended output vector. It goes through the first step where we create query, key, and value vectors for each token. Now to create this query, key, and value vector for each token, we multiply the input with matrices WQ, WK, and WV, and we get the query, key, and value vectors. The idea of query, key, and value is motivated from search retrieval, where user can type a query, and given that query, all the key pages will be retrieved, and what is the value derived from each page is the value, right? So for a query, which keys are important? So for a token, which other tokens are important? So each token will have its query, key, and value vectors, and to get those vectors we multiply with this matrix WQ, WK, WV, which is of size D model cross D head. Given that there are multiple heads, we call it multi-head attention. There can be 4 heads, 5 heads, and so on. Next, what we do is, as I was saying, for each query, which key is important, we can do a dot product of query and key vector. So each token has its own query vector, and if we concatenate the query vectors of all the tokens, it becomes a query matrix, right? So that's why we call Q, K, and V matrix, because these are of all the vectors. So we multiply Q with K, query with key, we get the weightage of each key for that query, or you can say that for each token we get the weightages of other token, how important the other token is. Let me give an example. Delhi is the capital of India, so Delhi and India are connected. Similarly, cats that eat were full, so were, because I have used cats, or cat which ate is full, so I am using singular cat, so that's why I am using each. And when I was using cats, I was using were or are. So this is how the words are connected, and cats will have a weightage more on are, cat will have weightage on is, and so on. So this is how the weightages game exists. So now when we do the multiplication of Q and query vector, we get the weightages of different words. We pass it through softmax so that these weightages are normalized between 0 and 1, and then we multiply it with the V vector of each word depending on how much weightage we have given to it to get the attended vector. Now this attended vector is again projected by multiplying with a W naught matrix to get the final attended vector. Now one interesting thing, the input vectors dimension was n cross d model, and also the self-attended output vectors dimension is n cross d model. Just the difference is for each token now we have attended output vectors. So this is how multi-head attention works. Now let's look at multi-latent attention. In multi-latent attention we do all this calculation but in latent space. So basically what, first of all, we know that to get the Q we need to multiply X with WQ, where X is the input vector. So if we multiply input vector with another matrix WQA, which is of dimension D model cross D latent, what will happen? This vector X will become of size N cross D latent. Initially it was of N cross D model, but now it has become N cross D latent. So what, let's say each input token had 32 dimension, now we have reduced it to 4 dimension. So that is what we have done, that we have done a dense representation of all the important features of that token in a condensed way. So what will happen? X will become of dimension N cross D latent. Now you will calculate Q, K, V, everything will be in that latent space, and the size of this matrices will become D model cross D latent. Previously it was D model cross D head, now it will become D model cross D latent. And also next you will do the attention calculation, and finally you will project it using one more matrix which is of D latent cross D model. An interesting thing is that finally when you project you will get back N cross D model only, which is same here. The output projection is same, just that all the calculations you have done in the latent space, right? Now what happened by doing calculation in the latent space? So in MHA you were directly projecting to D head, here you are projecting to D latent. Computation was happening in D head space, but here it's happening in D latent space. It's full dimensional matrix, here it's a latent dimensional matrix, so it's more costly because of more dimension. This is less costly. And if you see how much parameters we saved, in standard MHA we have WQ, WK, WV and WO matrix. Each is of size D model cross D model. So for 4 cross D model cross D model will becomes 4 into D square model. While in multi-latent attention all the calculations are happening in latent space, which is of D model cross D latent. And we have how many matrix? 1, 2, 3, 4. Again 4 matrix, which is 4 cross D model cross D latent. So since D latent is very much less than D model, we are able to save lot of parameters, and this leads to cost efficient and parameter efficient training. And also since the final projected vector is of same dimension, we are not losing on dimensions, which is like model is able to perform well, but all the calculations are happening in small latent space, reducing the parameters and also cost and computation. Next improvisation they did was mixed precision training. So we know what mixed precision training is. That is some part of the model will be trained in high precision, some part of the model will be trained in lower precision. So they utilized FP8 mixed precision training to optimize memory and computational efficiency. The core general matrix multiplication happened in FP8. FP8 means just with 8 bits, which is like an integer, just with 8 bits they were able to do all the matrix multiplication, while the critical components like embedding layers, mixture of expert gating, attention mechanism, they were calculated in higher precision, which is 32 dimensional. And let me tell you how this FP8 calculation happens. So you will have a FP32 variable, or like very precise number which is in decimals. In integer format you will convert it by doing some scaling. So you will do something like min max scaling, that how will these parameters, if you have to scale in some other space, what would the representation look like. For example, if you have numbers from 0.0001 to 0.0099, how can you represent them into just 100 values, 1 to 100. So you will do that scaling, right, scaling and projection. So that is what happens in this FP8 calculation. Now one problem that happens in this computation, which is also called quantization, you would have seen that you are able to download models with 4-bit quantization, 8-bit quantization. So this is what quantization is, that if you have very precise values, how can you represent it in integers with just 100 space, let's say 1 to 100, you just have 100 numbers and you have to represent 10,000 precise decimal points in just 100 numbers. You definitely, there will be some loss of precision, but you can always have this scale factors to map from one space to another. That is what quantization is. One problem that happens in quantization is, let's say you have all the numbers in a very smaller range or smaller space, but there are some outliers as well. So the quantization takes a hit because it's like a min-max scaling, right? So to handle activation outlier, they employed fine-grained quantization. That is, they did quantization at a 1 cross 128 tile wise space, preventing outliers from distorting overall precision. Outliers are extreme values. Instead of scaling the entire batch of data at once, having one scale factor, they split the data into smaller groups like 1 into 128 tiles. Each group is scaled separately, so an outlier in one group doesn't mess up the another group. So this is one more technique they used, and they used mixed precision training. What happened because of that? Some of the layers took lesser space because FP8 quantization will be using lesser memory and it will be faster, and some very critical components like embedding layer, mixture of expert gating, attention mechanism, they were done in higher precision space, which is FP32. In this way they were able to solve efficiently, have good results, as well as cost efficient and parameter and computation efficient training. Next thing, or next optimization they did was multi-token prediction. We know that all the sequential model do the prediction word by word, right? But DeepSeek R1 model, what it did was it predicted multiple tokens, let's say next 3 tokens. So they were able to predict not just single word, but words or subwords simultaneously, rather than just predicting the next single token. This approach enhanced the model efficiency and accuracy by considering a broader context and reducing the number of sequential steps required for generation. And one last optimization that I will talk about is the reinforcement learning. What they did was, and one last optimization that I would like to talk about is reinforcement learning. So they improvised the proximal policy optimization, PPO, to get a tweaked version of it, which is called group relative policy optimization, and this also saved a lot of parameters, and also the complexity reduced, and it resulted in faster efficient training. So let me explain what they did with group relative policy optimization. I will use this block to explain. So in group relative policy optimization, it's a reinforcement technique especially designed to enhance the reasoning capabilities of large language models. What is GRPO? It's an optimization over PPO. So what PPO is proximal policy optimization. It has a complex looking formula like this, where let me just explain what reinforcement learning does is it takes the model after the fine tuning, which is supervised fine tuning, and tries to optimize it further so that it is more aligned towards human preferences, like human would like to reason things, think, and then answer. So we want to tweak the parameters so that it's making the model more reasonable. Now this complex looking formula is for PPO as well. So what we do is we try to tweak the parameter from old parameters to the new parameters, which can better the reward, and reward here can be something like a model which is able to reason well and so on. Now one important thing is that there is this A involved here. A is like the advantage, or you can say the reward, by moving from old parameters to the new parameters. What is the reward we get? That is what A is. Now in PPO, what happens to calculate the reward? What you need to do is you need to estimate the value of each response. Like if model is in a particular state, what is the reward it is getting, and the new reward that it gets, how much more advantageous is that new reward compared to the basic value or reward it gets in that state. Now for this value estimation, there is a separate critic model, or there is a separate neural network model which estimate the value at each state or each parameter, you can say. Now what GRPO does is, it's a critic free optimization. It removes the need of that critic model, and it removes the need for critic model by comparing response within a group, significantly reducing computational overhead. Now we are talking about the group relative policy optimization. What is group? So what it does is, so what it says that instead of me having another critic model which will tell me that what is the reward at this state, and if I move my parameters towards a better state, how much advantage will I get, let me directly generate a bunch of responses, and the reward that I get for each response be the expected reward at that state. And what do we mean by generate a bunch of responses? So here's a very good example. The question is, what is the sum of 8 plus 5? Now there can be multiple ways to answer this. The answer is 13, it's 12, the sum is 13, something like that. Now we can generate multiple responses, and there can be a reward model which can reward each one of them. And how the reward will happen, it will be based on accuracy, the formatting, whether there is think tag or not, if it directly emitted the answer or thought it, solved it in a chain of thought or structured manner, how is the language, spelling correct or not. So there can be multiple rewards. So the reward for each one of them can be averaged out, that can become the expected rewards, and we can try to move towards the direction of a response which has better reward. So we know that the expected reward by grouping or averaging across multiple responses, and we can try to move towards a response which is better, whose reward is more. So we can try to tweak the parameters in the direction of highest reward. So that is what GRPO does. It removes the need for a critic model or an extra value function. So what it does is just simply generate multiple responses, do the automated rewarding of all of them, and it knows what is the expected reward. Now it will try to move the parameters in the direction of maximum gain, and that is how the model will start becoming more and more reasonable. The parameters will get started tuning themselves towards higher preference, how the human would prefer the answer. So they have shown the calculation, what is the mean, reward, standard deviation, and so on. And so this is the main idea of group relative policy optimization. One more thing, let me also tell the other details about the formula. So we know how this A is calculated. It is the advantage over the expected rewards, and the model will tweak the parameters. We also ensure that the parameters do not move a lot, right? If parameters move a lot, then there is a risk. So the movement is restricted by these clipping parameters, 1 minus epsilon, 1 plus epsilon, both in both the directions. And also there is a KL divergence, that is the model that we got after supervised fine tuning. The reinforcement learning adjusted model doesn't have very huge divergence from that model. So it is similar to the supervised fine tuning model, also some deviation and more in the direction of human likable response, but not too much divergence. So it restricts, that model doesn't diverge a lot from the state it was in after the supervised fine tuning. So this is the KL divergence formula. And if you have low beta, it means you are allowing more exploration, and if this parameter is large, it means you are not allowing too much exploration. You want to exploit just the nearby spaces with lesser deviation but better rewards. So that's what this is. And if we can summarize, reward, so critic requirement, there is no critic requirement in GRPO. In PPO there is a need for critic. Reward calculation is based on group performance. Here the reward calculation happens on a separate model, which is the critic evaluation model. And this is how the advantage is calculated, and advantage calculated in value based model is something like this, and so on. So you can read about it in more details. I will add the link of this blog in the description. So summarizing all of it, we saw that what are some advanced improvisation DeepSeek uses so that it performs on par with OpenAI's O1 reasoning model, which are like mixture of experts, multi-head latent attention, advanced quantization technique, multi-token prediction, and reinforcement learning. So these are some of the improvised techniques it has used so that it is able to train huge 671 billion parameters with just 37 billion activated parameters per token, because of this improvised techniques, the training is very efficient as well as cost effective and computation effective. So with marginal of the cost, just $6 million, it is able to train a model which is on par with OpenAI's O1 reasoning model. So hope you liked the video. Please like and subscribe and stay tuned for more such updates. Bye.